Let's continue with this introduction to the design of water supply networks with EPANET. Following the nomenclature in the US EPA manual, there are two different types of objects in our network: physical objects and non-physical objects. Amongst the physical objects, we can find node elements, such as junctions and reservoirs, which are water supply sources to the system, or tanks, which are intermediate storage facilities. Also amongst physical objects, there are arc-type elements, such as pipes and conducts, pumps, which are elevations, and valves. Now, amongst non-physical objects, we have demands, which are additional demands to the system, curves, which are patterns to model the behavior of the different elements in the network. These curves do not only correspond to pumps, they may also represent the filling and emptying curve of a reservoir or some other kind of information. And finally, we have patterns, which correspond to the demand and can be used in a modelization. EPANET models water supply systems as a series of arcs connected to different nodes. As we just said, arcs can be pipes, pumps, or valves, and nodes can be junctions, tanks, and reservoirs. The most usual elements in a network are node elements like junctions, connections. These are points in the network where different lines converge, or where there is a water inlet or outlet. The editor of the current slide shows the model of data for a junction element. We can see how to give a name to a connection. We can see the connection coordinates, as well as a possible description or ID label or tag, which is optional. We can see the elevation in meters of the connection compared to a reference point. We can also see the nominal water demand at the consumer junction, as well as a possible identifier to characterize the demand depending on the consumption pattern, the category, the number of categories of the different demands, and finally, we have the possibility to simulate this demand node as an emitter. Let's remind that emitters are pressure-dependent water flow outlets. This will help us simulate, for instance, sprinklers, water leaks, or even the behavior of fire hydrants. Initial water quality patterns, either with a specific quality level or an element introduced at one point in the network with a certain water quality. And finally, the last four fields: current demand, total head, pressure, and quality. They will obviously reflect the results of a simulation. The current demand, the total head, the pressure at this point, or quality pattern elements. That is why here, in this slide, these four fields appear as non-operational. We are still building up our model, and we still haven't got our simulation. Once we have built up our model and carried out our first simulation, these four fields will contain information and will display the values for the corresponding node. Another essential node element in any network is the reservoir, which is, in other words, an unlimited supply source for our system. Quite obviously, these supply sources allow us to model lakes, rivers, groundwater aquifers, or simply connections to other systems. Reservoirs are the natural border of the network, and their head and water quality cannot be affected by the system. It is a contour requirement in the mathematical model that we use. The data model of any reservoir includes the elements we can see in the slide. We can actually give a name to each element, and this name can be a number. As we can see, number 1 would be an example of a name in an alphanumerical system. So for reservoir number 1, we have the corresponding coordinates, x and y. We have optional comments or descriptions. We have the total water hydraulic head in the reservoir, the possible behavior pattern to model the head time variation, and if we are using quality parameters, we also have water quality level in the elements at the start of the simulation and water quality entering the system at a specific location. Quite obviously, the last 4 values, net inflow, elevation, pressure and quality, are not yet available, since we still have not run our simulation. Tanks. Tanks are other types of optional node elements which act as storage, where the stored water volume may vary with time throughout the simulation. Tanks are limited by their maximum and minimum levels. EPANET stops water flow inlets whenever the tank has reached its maximum level, and it will stop the flow outlets when it has reached the minimum level. Tanks may also act as water quality sources. The data model presented in this slide allows us to assign a name to a tank, to locate it horizontally and vertically, to add descriptions or identifiers, and to assign an elevation in meters of a water column. We can also assign patterns of initial level, maximum and minimum level pattern, or even a diameter. In the case of rectangular tanks, the equivalent diameter will be 1.128 times the root of the section. We can set minimum water volumes in the tank when the tank is at its minimum level. Or we can use a volume curve to describe the relation between the tank volume and the water level. Tanks obviously incorporate quality models, and therefore the type of mix inside the tank, the fraction of the tank total volume devoted to a 2-compartment model, or the reaction coefficients within the tank, as well as the water quality levels, or water quality entering the network. All these parameters will be defined at this point. As in previous cases, the last 4 elements of the data model refer to the simulation. And since we have no simulation yet, we have no results. Pipes. Pipes are arc elements which transport water from a point in the network to another. EPANET assumes that the pipes are full at all times. The flow direction is the following: from the highest hydraulic head to the end of the lowest pipe, always following the decrease in height. The most important hydraulic parameters for the pipes are all those presented in this slide, such as, once more, the name we assign to each element, the node name at the inlet and outlet of the pipe, inlet and outlet from a graphic point of view. We have already mentioned and shown that water will always flow from the highest pressurized node to the lowest one. These nodes can of course be different, depending on the simulation and on the demands. We can also include identifiers, descriptions, and comments about the pipes, and we must also include the real length of the element, the diameter in millimeters, and the roughness coefficient of the pipe, which will depend on the formula we have previously set in the program preferences. That is, Darcy-Weisbach, Hazen-Williams, or Shazy-Manning. We can also add a minor loss coefficient, and we can use initial status elements to specify whether a pipe is open or closed at the start of the simulation. We can include quality model parameters such as the pipe bulk reaction coefficient and the wall pipe reaction coefficient. The parameters obtained as a result of our mathematical analysis are the ones in the last 7 fields. They are empty right now, of course, since we have still not carried out our simulation. Before moving on, I would like to mention very briefly the different calculation methods we can use. First of all, there is the Hazen-Williams method. It is mostly used in the Anglo-Saxon world. It cannot be used with any other fluid than water, and it was originally developed for a turbulent regime. The Darcy-Weisbach method is the most accurate one in theory. It applies to any fluid in any regime. And lastly, there is Shazy-Manning method, the most widely used, but generally for open flow channels and not so much for pressurized pipes. And finally, reference must be made to minor losses. The importance of including them or not will depend on the planned distribution of the network and on the required accuracy. They can be calculated by assigning a minor loss coefficient to the pipe, as we have seen before. This coefficient will multiply the term of the kinetic energy in the pipe. That is, it will multiply the square velocity divided by 2 times the gravity. Pumps are another arc element. These are elements which transfer energy to the fluid in order to increase its hydraulic head. The most important characteristics of a pump are the inlets and outlets, and the pump's curve, which is actually the relation between head and flow. The most important outlet parameters are water flow and load. Water flows in one direction inside the pump, and EPANET does not allow one pump to work out of the range provided by its own curve. The speed variation of pumps can also be taken into consideration, and be determined and modified under the previously described conditions. By definition, the characteristic pump provided by the program has a speed character of 1. If the speed of the pump doubles, then the relative setting of the character will be 2. If the speed halves, then the character will show the value 0.5. A change of speed implies a change in the position and shape of the characteristic curve. Just as pipes, pumps can be activated or deactivated instantly. Additionally, it is worth mentioning that EPANET can take into consideration energy consumption and the cost of the pump. Every pump can have an efficiency curve and an energy price list assigned, and the current slide shows all the pump elements we can see in the data model. Pump and node names, optional ID labels and descriptions, the characteristic curve, the power supply, the relative speed, the time pattern controlling the pump operation, the initial status, the performance curve, the price of energy in monetary units, and the time patterns to describe the variation on the energy price throughout the day. The last 4 elements are, once more, the result of a future simulation. The last element or physical object in the EPANET is the valve. Valves are used to reduce the pressure and/or flow at a particular point in the network. Valves are arc elements. And here is where those who come from the real world and know about valves need to use their imagination. Valves are not really arc elements. In fairness, they are clearly node elements. Valves are quite specific elements, located at very specific points. And this is where we need to learn and understand that, in reality, these elements that regulate the flow are again specific and can be associated to node elements. However, in the mathematical model, they behave like arc elements, since they regulate pressure or flow from a node to the next. They set a difference in pressure from a point to another. They set a difference in flow from a point to another. And this is obviously what an arc does. Therefore, the mathematical model for valves will be an arc element. EPANET can simulate different types of valves depending on their purpose, to reduce or maintain pressure, to break pressure, to control flow, to throttle, or simply general-purpose valves. Valves can perform their specific control status if they are completely open or completely shut. The status of a valve and its preset limits can be changed during the simulation by using the status options. And in the data model of the current slide, we can see that we can assign names to every element and their nodes, up and downstream. There are optional fields for description and tags, and there is the diameter, the type of valve, amongst the 6 categories previously stated, the operational setting of the valve, as well as possible loss coefficients, or the valve condition at the start of the simulation. As a result, we obtain 5 more fields, which are again empty right now, since we have not yet carried out our simulation. And well, besides the physical objects we have stated previously, EPANET also includes non-physical objects. In the first place, we have curves, which represent the relationship between two pairs of data through magnitudes or quantities. Two or more objects can be part of the same curve. With EPANET, we can use the following types of curve: a characteristic pump curve, an efficiency curve, a volume curve, or a head loss curve. The pump curve itself can in turn be defined as a single point, 3-point, multi-point, or variable speed pump curve. We will not go into detail about each of these curves and how to operate with them. Efficiency curves determine the performance of a pump as a function of its flow. They are only used for energy calculations. Whenever there is no specific efficiency curve for a certain pump, a default generic curve will be used. Volume curves determine the water volume variation in a tank as a function of its level. They are used when the variation of a tank cross-section, depending on its head, has to be accurately represented. The minimum and maximum water levels represented by this curve must be the same as the minimum and maximum levels in which the tank works. Head loss curves are used to represent losses in a general-purpose valve as a function of its flow. This allows us to model devices and situations and provide specific data on flow losses of flow control valves, reverse flow control valves, turbines, and dynamic head reduction valves in sinks. The following slide tells us about the curve editor, which is a dialog to define the curve type and to edit values describing the behavior of different parameters. We can see here all the fields: ID label, description of curve representation, type of curve, data, the resulting equation, and a curve graph. Other non-physical objects which are very interesting for an EPANET simulation are time patterns. Time patterns are a group of multipliers which are applied to quantities in order to represent a variation over time. Node demands, reservoir heads, pump schedules, and water quality sources can have associated time patterns. The time interval used in all patterns is a fixed value set by the time options of the project. Within this interval, the associated quantity remains constant and equal to the product of its nominal value and the factor during this period of time. Moreover, all time patterns must use the same time interval. Each can have different number of periods, but all must have the same pattern. When the simulation clock exceeds the number of periods in a pattern, the pattern is reset to the first period. For example, let's consider a junction node with an average demand of 20 liters per second, assuming a time interval of 4 hours. Throughout the simulation, the real demand in the node would be as follows. In this slide, we can see a screenshot of the time pattern editor, which is a dialog to define the multiplier values for each interval of the time pattern. We must provide the identifier, the description, the factor, the time interval. And finally, this time pattern editor will show all these fields in a graphic representation. To finish this teaching unit, where we have reviewed all the physical and non-physical objects that an EPANET project includes, we will now talk about the controls of our network. Controls are instructions setting how the network operates over time. Controls specify the behaviors of selected lines as a function of time, tank water levels and pressures at specific points in the system. There are two types of controls: simple controls and rule-based controls. Simple controls are based on the tank water levels, pressure at junctions, times in the simulation, and times of the day. There is no limit on the number of simple controls. Whenever they represent water levels, controls are expressed as the level of water in the tanks above the bottom, and not as total heads. It must be reminded that using two or more pressure controls for a single element can result in an unstable system if the pressure characteristics are too close to each other. If this is the case, the best is to use a couple of rule-based controls to avoid instability. Additionally, rule-based controls set the state of an element and its characterization through a combination of conditions that could occur in the system once the initial hydraulic status has been computed. In rule-based controls, we can add basic programming rules, such as conditions and their results. These rule-based controls are obviously one step forward in the way we program and control our network. For both simple and rule-based controls, the behavior of arcs and nodes can be specified. And here is the end of our teaching unit on how and under which criteria we can build a basic network with EPANET, and how to make everything work properly.